In this video, we're going to begin to look at hemoglobin and myoglobin. Hemoglobin and myoglobin are the proteins in your body that will store and transport oxygen. So we're going to look at everything to do with those proteins, including binding constants and the mechanism behind binding oxygen. We're going to start with myoglobin, and myoglobin is a protein made out of one peptide chain, and it has 8 alpha helices that are labeled A through H as seen here. And if you see letters like A, B, E, F, this is the connection between our helices. And what myoglobin does is it helps our muscles get oxygen, and this is incredibly important for mammals that live underneath water or any aquatic animals. They have about a 30 times increase concentration of myoglobin. Now if we look at myoglobin, it contains what we call a heme group, and a heme group has an iron molecule with a porphyrin ring surrounding it. So this is our heme group. Here's the iron and the porphyrin ring. Now it's this heme that binds oxygen, and so when oxygen is bound, it's interacting with His on E7. E is what alpha helix, so it's the 7th residue of alpha helix E, and we have a hydrogen bond there. Valine E11 and phenylalanine CD1 is help positioning this heme ring, and heme can also bind to carbon monoxide, nitrogen monoxide, and H2S. In fact, carbon monoxide actually binds 200 times more efficient than oxygen. That's why you should have carbon monoxide detectors in your house, because we can't smell it, we can't notice it, we can't see it, but it will suffocate you by outcompeting oxygen in myoglobin and in hemoglobin. Here in this photo, we have another look at our porphyrin ring. You can see this ring structure, iron in the middle. Histidine F8 is right here below the heme, and we have oxygen interacting with the iron. Now let's look at binding of oxygen in myoglobin. And we're going to look at what's called the binding curve of this event, but first we have to go through the logic of how we can come up with a binding curve. So we're going to start with the simple chemical equation of myoglobin, unbound, plus oxygen can go to bound myoglobin. And this is a reversible reaction. We say the dissociation constant, that is how much myoglobin will be free and how much will be bound, that's equal to the free myoglobin multiplied by oxygen divided by the myoglobin oxygen compound. And you can kind of think of, okay, like I said, how much myoglobin is free to bound. It will also give us a rate for how fast this event happens. And with that in mind, let's bring up a new variable that we call fractional saturation. Fractional saturation says how much myoglobin is bound to oxygen, and this number ranges between 0 and 1. 0 if no myoglobin is bound, 1 if 100% of myoglobin is bound to oxygen. And so our equation for this is bound myoglobin divided by the total amount of myoglobin, that is free myoglobin plus bound myoglobin. Now we can take our dissociation constant and our fractional saturation equations, and we can combine them. And what we see is that the amount of bound myoglobin is equal to free myoglobin multiplied by oxygen divided by K. Actually, what we're doing here, we're just rearranging the dissociation constant. In the next step, we combined our two equations. Got a little ahead of myself there. So fractional saturation is equal to this mess here, but what we can do is we can factor out free myoglobin divided by K from each side of the equation. And what we see is that the fractional saturation, that is how much myoglobin is bound, is equal to how much oxygen there is divided by K, which is our dissociation constant, plus how much oxygen there is. And that's nice because we can determine how much myoglobin is bound just by the pressure of oxygen. We don't need to worry about the amount of myoglobin that we have. Another way to express this is, since oxygen is a gas, we can just say pressure of oxygen, because if you remember back from general chemistry, concentration of a gas is equal to its pressure. And when we make that equation, what we see is that we get a hyperbola. That is, if we plot our fractional saturation of oxygen versus the pressure of oxygen, we get this curve. Remember, fractional saturation goes from 0 to 1. And so at very low pressures of oxygen, no myoglobin has oxygen bound. At high pressures, nearly all of the myoglobin has oxygen bound. And so how steep this curve is, actually increases when we decrease K. That is, the lower value of the dissociation constant, the tighter our binding. And that's important to remember, because in biochemistry, when we talk about strength of binding, when it comes to like drugs, pharmaceuticals, or any ligand, we will use this value of K for dissociation constant. So the lower the value, the tighter the binding. Now, when our PO2 equals our K, we say myoglobin is half saturated. So if we have a curve like this, what we want to do is we want to find where fractional saturation is 0.5. We go to our curve and then drop straight down. Whatever our pressure of O2 is at that pressure, whatever number we read right here, that's what our dissociating constant is. So one way to say that mathematically is that our fractional saturation equals PO2 divided by K plus PO2, where P is pressure again. At half saturation, the pressure of O2 equals K, so our equation is actually pressure of O2 divided by 2 PO2. So another way to say that, when K is equal to your pressure of O2, half your molecules are bound. We call this P50. So P50 is the pressure, in this case, the pressure of oxygen you need for half your myoglobin or your macromolecule to be bound. Myoglobin, if we look on this plot, P50 is 2.8. If we actually think about pressures of oxygen in the body, in your arteries you have 100 torr, while in your veins you have 30 torr of oxygen. What that means is, if myoglobin was in your blood, it would always be bound to oxygen, which is a bad thing because we need these molecules to give oxygen off to our various cells. So myoglobin isn't the protein that transfers oxygen in our bloodstream. Rather, it's the protein that will give oxygen from the capillaries to the muscle cells. Because muscle cells that are working hard, their pressure of oxygen will be very low, and this will cause myoglobin to release their oxygen. And in the next videos, we will learn about the protein that takes oxygen and travels with it in our blood, and that's called hemoglobin. But that's it for this video. I will see you in the next video.